Look closely at the shock diamonds in this exhaust plume. Every liquid rocket engine must solve a strict thermodynamic problem: how to power the internal pumps without throwing away the exact liquid meant for thrust. To force liquid fuel and oxidizer into a combustion chamber at hundreds of bar, the engine requires massive, dedicated mechanical power generation. The thermodynamic arrangement engineers choose to drive those turbopumps defines the engine's entire power cycle, setting its absolute physical limits. And that brings us to the core metric of engine efficiency: specific impulse. Maximizing specific impulse directly requires increasing the combustion chamber pressure. This diagram shows exactly how specific impulse works. It calculates how much thrust is produced per unit of propellant consumed every second. A higher specific impulse means the vehicle requires less total liquid to reach orbit. When a rocket is constantly fighting both gravity and atmospheric drag, extracting even a few extra seconds of efficiency translates into a drastically heavier payload capacity. But to squeeze out those extra seconds, the engine must force more mass into the chamber at higher velocities, steadily raising the internal pressure. The quest for orbital efficiency is an engineering war to achieve and sustain maximum chamber pressure without detonating the hardware. This schematic illustrates the legacy solution, the gas generator cycle. Here, engineers tap off a small percentage of the total propellant flow and route it into a separate preburner. The resulting hot gas from that preburner spins the turbopumps, but that exhaust gas is then discharged directly overboard at low pressure. It entirely bypasses the main combustion chamber. The SpaceX Merlin engine on the Falcon 9 rocket relies entirely on this architecture. By discharging that gas early, the engine loses the remaining energy it carried. In fluid mechanics, this is known as the tap-off penalty. While mechanically simple and highly reliable, the gas generator cycle represents a thermodynamic dead end. Constantly throwing away a fraction of the mass inherently caps the maximum achievable chamber pressure. This schematic shows how the staged combustion cycle solves the tap-off penalty. Instead of dumping it, the system routes the exhaust directly back into the main combustion chamber. By closing the loop, the system recovers all the remaining energy from the pre-burned gas. The Space Shuttle main engine, the RS-25, utilized this cycle to achieve a leap in efficiency. However, routing all the necessary mechanical power through a single preburner concentrates a severe heat load onto one turbine, pushing the metallurgical limits of components. This diagram outlines full-flow staged combustion. Its defining feature is the use of two preburners operating simultaneously. The entire fuel supply runs through a fuel-rich loop, while 100% of the oxidizer passes through an oxidizer-rich loop. Because every single molecule of propellant passes through a turbine before reaching the main chamber, no mass is discarded, and all thermodynamic energy is recovered. To power this architecture, SpaceX selected liquid methane and liquid oxygen, combined as methalox. Unlike the kerosene-based RP-1 fuel, liquid methane burns clean. It prevents the rapid buildup of carbon coking that can destroy intricate turbomachinery over time. Compared to liquid hydrogen, liquid methane has a much higher density and a boiling point closer to liquid oxygen, significantly simplifying the internal tank architecture. Liquid methane also provides a direct interplanetary advantage. Using a Sabatier reactor, atmospheric carbon dioxide and water ice can be synthesized into fresh propellant directly on the surface of Mars. Methalox represents an optimized intersection of thermodynamic performance, hardware reusability, and in-situ resource utilization. This animation illustrates the primary thermal advantage of the full-flow cycle. The massive heat load required to drive the pumps divides evenly across two distinct pathways. Because the work is split, the engine hits its total power target while drastically lowering peak turbine inlet temperatures. This reduction in operating temperatures directly lowers the metallurgical stress on the engine's hottest internal components. Legacy staged combustion engines ran so hot they required extensive, expensive refurbishment campaigns after every flight. Lowering peak temperatures without sacrificing total power output is the absolute mechanical prerequisite for zero refurbishment reusability. Recovering all that exhaust energy through a closed dual-loop system yields unprecedented combustion chamber pressure. Raptor 3 sustains an operating pressure of 330 bar, the highest of any operational rocket engine in history. This pressure metric surpasses both the RS-25 and previously dominant high-pressure Russian designs. At sea level, Raptor 3 delivers a specific impulse of 350 seconds, generating roughly 280 tons force of thrust. Across generations of development, engineers systematically stripped away external piping, sensors, and structural mass. Driving chamber pressure up while relentlessly cutting physical mass compounds the engine's efficiency, maximizing the vital thrust-to-weight ratio. Full-flow staged combustion was long considered practically impossible to build. The Soviet RD-270 attempted the design, but the program was discontinued before it ever flew. SpaceX transitioned this highly complex thermodynamic cycle from theoretical white papers directly onto a mass production schedule. Doing so required an intense, continuous test campaign to physically validate the violent fluid dynamics of two intersecting preburners. Post-test teardowns and physical inspections verified that the Methalox propellant leaves the internal chamber liners completely intact under immense thermal stress. Starship flight tests now supply active hardware data, proving that these complex engine relight sequences function reliably in a vacuum. Overcoming the practical manufacturing difficulties of this power cycle marks a definitive new baseline in aerospace mechanics. Maximizing thermodynamic efficiency via full-flow stage combustion is now viable at industrial scale. These specific engine metrics directly enable the heavy lift and turnaround requirements of full vehicle reusability. By compounding extreme specific impulse with an engine that requires zero refurbishment between launches, the cost per kilogram to low Earth orbit is forced downward. This drop in cost makes deploying dense satellite constellations and heavy orbital infrastructure economically viable. Raptor is the mechanical enabler for sustainable human expansion into the solar system. To dive into the actual math and first principles breakdowns of these thermodynamic power cycles, explore the systems engineering case studies on our platform. Thank you for watching.